Well, let's talk real quick about Cal 1. So if you could summarize Cal 1 for me, what are some main points from Cal 1? What are derivatives, right? Derivative. The derivative was the rate of change, right? Instantaneous rate of change. And we did a lot of things with derivatives, right? Okay, anything else that sticks out from Cal 1? How about things you didn't like so much in Cal 1? Limits, your professor, okay. Limits. Chain rule, okay, so that maybe would fall under derivatives, but that was an absolutely important rule, right? You had to know. Related rates. Oh, yeah. Oh, yeah. Related rates and optimization. Related rates. That was like, you know, a sphere is growing at a rate such that blah, 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 right? And then optimization. I'll just put optim. So that's like, you know, the farmer builds the fence and wants to use the least amount of material and blah, 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 right? Okay? How about geometrically? I heard Auntie. We'll get to that in a second. How about geometrically? Like, what did the derivative represent for us in Cal 1? Slope of the tangent line, right? So if we have a graph of a function, right, here's x, and you know, here's f of x, and if we say, well, what's the derivative of the function at a, then this would give us a numerical answer, right? We would go to some value, whatever it is, a. We'd go up onto the graph. We'd imagine a tangent line, right, to that graph. This numerical answer represents the slope of that line, right? That's geometrically what was happening with the derivative. Anything else you can remember from Cal 1 that you liked or didn't like? Or I heard antiderivative. You probably got that towards the end of the semester, right? How many of you did touch antiderivatives in Cal 1? Just a little bit. All right. Riemann sum. Did you do Riemann sums? Okay, good. All right, so I'll touch on Riemann sums in this class a little bit. We won't go real heavy into it, but we will talk about it because it's important. Okay, so that's I'll let that be the summary of what Cal 1 was, even though it's kind of short. So what is Cal 2? Well, if in Cal 1 we brought up the idea of the derivative, in Cal 2 we're going to have the antiderivative, which is going to be the reverse process of taking a derivative. So when you take a derivative, we know what to do, right? It's usually going to use some sort of rule, power rule, product rule, quotient rule, chain rule, something like that. And we get some answer when we take a derivative. In Cal 2, one of the main topics is taking antiderivatives or finding antiderivatives, which means going backwards. And this can be very difficult to do. And so we're going to spend the first all the way through almost to March. March 1st is when we actually stop figuring out ways of taking antiderivatives. So we've got a good month and a half of just solid, like, how do you go from something backwards, right? All these techniques. And that's where the homework and the practice comes into play, because you have to see how the processes work, and hopefully it becomes kind of second nature to you, but you can only get that through exposure. So, and then what we'll do is we'll tie some geometric meaning to this, and we'll determine that when you're actually when you have a function, we know the derivative is a tangent line, we'll figure out that the antiderivative is somehow connected to the area under the graph. And then once we understand that that's possible, then we can really blow the doors open and we can start doing a lot of crazier things like taking that graph and rotating it. Like, imagine it's two-dimensional, right? It's on a flat sheet of paper, but if we take it and we rotate that around, let's say, the x-axis, it would create this solid. And, you know, the solid might look like, let's see, something like this. Right? Can you all kind of see that? Here's the x-axis going through the middle. We rotate that around. And this solid is three-dimensional, has a volume to it. It has a surface area, right? There's a lot of different things that we can now talk about. And so we'll go try and figure out, what the volume of that is and what the surface area of it is. We'll also investigate taking this graph and, taking it from here to here. Forget the area for a minute. We'll take it off the graph. We'll take it off the piece of paper. We'll straighten it out, stretch it out until it's nice and what? Straight? Taut. What's the word I'm looking for? Taut. Okay, taut. And then you measure it. How long is it? And that would be the arc length of that. And that, believe it or not, is a lot harder to do than rotating it and finding the volume. So we'll investigate that. I already talked about surface area, which is if you wanted to paint the outside of this, how much paint would you need? And I'm just summarizing here. There's a lot more involved in this, but just to give you an idea of where we're headed. And then we get into Chapter 8, which is the most critical chapter, right? So for those of you who have experienced Cal 2 already, Chapter 8 is going to be that's where you separate the men from the boys. So I'm not trying to be sexist, but you've heard that before, right? I mean, that's where you really get challenged, all right? And that's series, and we'll just get there when we get there, okay? There's a lot in there I don't want to talk about. Just know that it's going to be fun, all right? All right, where's my little list? That's it. I'm ready to get into this, unless you have any questions or comments. I felt like that was a very poor, get you motivated for Cal 2, But what I think is more important, because I do a lot of reflecting on what is it that Cal 2 gives you. Like, what's the value of Cal 2 for where you're headed? Because not everybody's doing the same thing, right? How many engineers do we have in here? All right, so a lot. How about computer science? Any math majors? Okay, so yeah, maybe. All those fields are different, and I can tell you that a lot of what we do in here, in your field of engineering or computer science, or even as pure mathematicians, that's a little different because you never get to rely on a computer too much to do your work for you. But in engineering, everything that we do in this class can usually be done with a computer. And in computer science, you actually write the programs to do what we're doing in here. So, what is the value of actually going and doing this, right? I mean, that's a common question. And so I want you to look at this more about not so much the material that's within Cal 2. Look at it as what are you capable of learning? Okay, can you learn this material or not? I mean, it's regardless of whether or not it's important later. This is a challenging topic, and if you can get through this successfully, you can notch that out in your belt, Cal 2, and it means something. It means something to someone who wants to hire you. It means something, on your degree. That Cal 2 is important because this is a high level of thinking in here compared to anything you've done. All right? So that's the value of it. It's maturing as a learner more than can you find the volume of a solid rotated around the x-axis? I mean, you know what I'm saying? Okay. So let's all keep that in mind as we move through. I have some warm-up exercises for you. Everybody ready to warm up? All right, I'm just going to put some problems on board. I'm going to let you work on them for like 10 minutes, see how far you can get with these. I'm not going to collect these. I thought about doing it like as a quiz first day, but then I was like, no, they're going to get the wrong impression. So y is equal to the natural log of x. I want you to find y prime. Or if you don't like that notation, I want you to find dy dx. And 2, I'm going to write the equation xy squared equals sine y. Find, same thing, y prime. Number 3, this is a right triangle. 2, 7, x. Find x. Number 4, another right triangle. Theta is this angle up here. x1 square root x squared plus 1. Find secant theta. So I'd like for the first 5 minutes or so for just you to do this without talking to anyone. And then what I'll do is I'll open it up and you can talk to each other. All right? Any questions on what I wrote up here? This is a 7.
Yes, sir.
Yeah?
On number 2, on the right, equal sign, what's that first?
Sine.
Okay.
So this is sine y. I write in all caps all the time. So if you don't know how to do number 1, go to number 2. If you don't know 2, go to 3. Don't know 3, go to 4. Don't know 4, well, you had a good break, I guess.
Oh, yeah.
You had a real good break. All right, are y'all ready to make some friends? Yeah? All right, so y'all can have another 5 minutes. Y'all can talk to each other. And if you want to know who your neighbors are, just look down. They've got their names right in front of you. So.
Some of this stuff like algorithms and math.
Okay.
Yeah, you're right. I think I'm ready to go.
Okay, good.
I'm ready for this.
All right, let's go through these, all right? I would hope that you working on your own, you had a certain feeling. And then when you were working with other people, hopefully that feeling got better. Hopefully. And I would hope that at this point you know that working in groups on mathematics is usually much better when it comes to learning than trying to work by yourself. All right, so I can't force you to form groups and schedules and people, when they work and when they have other classes. I know that that conflicts, but I leave it on you to try and figure out who in this class you can study with, and you'll have to do that yourself. Unless we want to spend like 20 minutes saying, okay, how many of you are free on Monday at, we could do that if it really needs to happen, all right? I've done it before. I know some of you had me for college algebra, and we did like Survey Monkey, right, or something? We did Survey Monkey, and we did like everyone filled in their schedules, and then I don't think anyone did anything with it, though. That's why I'm not doing it. All right, what's the derivative of natural log of x? 1 over x, okay. As long as you remember that. All right, number 2. You have x y squared equals sine y. You're asked to find the derivative. So you cannot solve this equation explicitly for y. You can't get y by itself on one side. So this is called an implicit equation. And so we have to use implicit differentiation, which means we take the derivative on both sides of the equation. Here, because of what I asked, with respect to x, which means we treat x like it's the independent variable, and we treat y as if it depends on x, which means that the derivative of x, anywhere we see that in here, would be what? 1, and derivative of y would be y prime or dy dx. And this is where it's going to matter, like your class before this, what notation they used. But let's go ahead and take this derivative. So we're taking the derivative of this with respect to x, right? That's what we're doing. The left side of the equation, we have to use what? Product rule. There's a product right there, x times y squared. So the derivative of a product is the derivative of the first factor, which is x, which would be what? 1 times y squared, and then plus the derivative of y squared, which is 2y times y prime. And that's the trickier part, because when you take derivative of y squared, the 2 drops. But then you have to take derivative of the base itself, which was derivative of y, which is where you get the y prime from. But then you have to finish off by multiplying by x, and that completes the product rule. And that's the derivative of the left side. The derivative of the right side is what's the derivative of sine of y? Cosine of y. But again, because of chain rule, we have to take derivative of what's inside, and derivative of y is not just 1, it's y prime again. So we get times y prime. Now, some of you, again, came from a class where they may have, instead of using y prime, used dy dx. Anybody use that instead? That's the same thing, right? You understand that? All right, and then you would go through the process of isolating y prime, right? You get all your y primes on one side, everything that doesn't have y prime on the other, factor out a y prime, divide through, you've got it. I'm not going to continue it. That's the most important part of it. All right, any questions on that? All right, number 3. That was not a trick question. It was just solving a right triangle. So you need to know the Pythagorean identity, right? A squared plus b squared is c squared. So you could say 2 squared plus x squared is 7 squared, right? And just, right. X squared is 45. X is square root of 45. Plus or minus?
Because you took the root, so yeah, right?
Yeah, so we run into a little bit of a question here. So let's just take a vote. And I'm not trying to call people out. Is it plus or minus? Yes? It's all right to put your hand up.
Technically, but
Okay, so we have to always understand this in mathematics, the context of the problem. If this triangle wasn't here, and that was all I asked you, you would have to put plus or minus.
Right, yes.
But because this equation came from this triangle, we are eliminating the possibility that x could be a negative number, because we're assuming it's the length of a side of a triangle. So yes and no, but in this case, no because of that, right? So this is fine, and we could simplify that if we want. That's it, number 4, or number 3. Number 4, I don't remember drawing it this way, but okay. Is that what I had? So I asked for secant theta, which is the same as 1 over cosine theta, right? It's the reciprocal of cosine. And cosine of an angle on a right triangle is which side over which side? Adjacent. So what's the adjacent side to theta in this triangle? 1, right? That's the adjacent side. And divided by the hypotenuse, which would be this one, but then flip it over because 1 over it. So what's the answer? Just root x squared plus 1 over 1, which is just that. That's it. All right, so the reason why I gave this to you as a warm-up is because pretty much everything that I did in this problems 1, 2, 3, and 4, you will need in order to do what we're going to do right now, today. But all of this is what would be considered prerequisite material. I mean, this is stuff you should already know how to do, right? So as we proceed through the class, that will continue to happen. And stuff from the past will continue to be pulled out, but I won't spend the first 15, 20 minutes of class every day going and pulling all those out and saying, remember this, remember this? All right? It'll just be right there in front of you. And so if you don't understand it, you'll have to go back and review on your own. I put my office hours up here because I thought it would be important for you to know when you can come and get help. And for Cal 2 class, I usually get a good group of students that come on a regular basis. Hopefully that'll happen again. I'm in my office Monday, Wednesday from 9 to 12:45. And then for Tuesday, Thursday, I'm here before our class for about an hour, almost 2 hours. On Friday, I'm here by appointment. Immediately after this class, I have another class. And then after that, I am free, but I don't have any official office hours. So what I would like for you to do is, if none of these office hours work for you, and there's something that works a little later in the afternoon on either of those days, I'd like for you to email me. And if enough students email me saying, hey, you know, Tuesday, Thursday, 3 to 4 would be better, then I will change my office hours. But that's going to be on demand from you. I'm not going to switch it, just not going to guess, right? I have to have some feedback. And I'm going to tell all my classes that. So some alternative times to consider would be Monday, Wednesday, 3 to 4, or Tuesday, Thursday, 3 to 4. I'm willing to do something like that, one or the other, but not both. So if either of those look better to you than this, just email me, all right? I do take attendance, so this is our sign-in sheet. Those of you who've had me in the past know I'm very terrible when it comes to remembering to hand this out. I'll do my best. So there's the date across the top, and then your name, initial in the box, pass it along. And then there's one more thing, and then we're going to start the first notes of the semester. On the syllabus, there's a policy on cell phones and computers and things like that. So even though it's in the syllabus, I'll just point out today, you're not allowed to be sitting there texting on your phone or do any of that, right? Anyone remember the penalty for it? 10% or 10 points off your next exam, whichever exam that is. And you'll be asked to leave and counted absent for the day. And you only get 4 absences. So if it's so important that you need to be there, then just get up, go out there, do it, come back. All right? That sound fair? Now, if you're expecting an important phone call, I know it happens to me a lot, just let me know, before class, and I don't mind you having the phone out. But then if you do get that call, I do ask again that you take it outside, and I'll do the same for you. All right. Here we go. So we're going to start in Chapter 3, Section 5. The notes that I'm going to be going off of are up there on the projector. Those are located on Canvas under Course Files, and those can be printed out, brought to class, or you can actually have them on your tablet, and you can have that in class. That's fine with me. I don't have notes for the entire semester, but enough for us to get started. So we're going to start talking about one-to-one functions and the inverse trig functions. Do y'all remember the inverse trig functions from pre-cal? You start off in pre-cal, you have 6 trig functions, right? Y is sine x, y is cosine x, tangent x, and then you have all their reciprocals, right? I'll put the reciprocals next to them. What's the reciprocal of sine? Cosecant, and then secant, cotangent. All of these functions are continuous on their implied domains, meaning that if you draw them, it's nice and smooth, except for where you possibly have some domain issues. Like, which of these have domain issues, like problems in their domain? Tangent has some problems, right? At pi over 2, negative pi over 2, and it's periodic, so it happens it's pi over 2, but then where's the next one? How far away is the next discontinuity? It's pi, right? So it has a discontinuity every pi. If you graph it, then you would see it. I'm going to show you the graph in a second. So the tangent, cosecant, secant, and cotangent, these all have domain problems. Sine and cosine are nice and continuous on their entire domains. All right? And so you learn about those in pre-cal, and then you say, hey, look, for each of those 6 functions, there's an inverse function. And you learn about those in pre-cal also. So you learn about inverse sine, and there's 6 of them. That's what we're going to start with here. But to do that, I'm going to actually go back, almost like we're in pre-cal, just to get your brain going again, and talk about what does it mean to be an inverse function. And then guess what we're going to do, because this is calculus. In Cal 1, we had these 6 functions, and then we talked about what their derivatives were, right? Derivative of sine is sine of x, cosine x. Derivative of cosine x is negative sine x. Derivative of tangent of x is secant squared x. Is that important to know that, Zach? All these different things? Yeah. Derivative of cosecant x. Derivative of secant x. Secant x tangent x. Derivative of cotangent x. Negative. Okay, so if you don't know them, that's okay, but where are you going to go find them? There's formula sheets, right? They're also on our website, on Canvas. You're allowed to print those out. You're allowed to bring those to class. In fact, I suggest that you bring those to class every day. You can use them on any assignment I ever give you. I will never take those formula sheets away from you. And they have all the derivatives of these there. But as time goes on, these will have to be put into the memory at some point because it'll just become so repetitious. So we have the 6 trig functions. We have their derivatives from Cal 1. But even though you learned what this was in pre-cal, did you ever learn what its derivative was? No, right? So that's where we're headed. But let's first just talk about the inverse trig functions. So what is a one-to-one function? I'm not asking. I'm just asking you to look, I guess. One-to-one functions pass basically the vertical line test and horizontal line test at the same time. Right? So if you graph a function, let's say that right there, that's a function, isn't it? It's a parabola. Passes the vertical line test. Does it pass the horizontal line test? No. So it does not have an inverse. It is not a one-to-one function. So it must pass both the vertical and horizontal line test for it to be one-to-one. And only one-to-one functions will have will be invertible. We'll be able to find inverses of. So here are the 6 trig functions. There's your sine function. Right now I'm only looking between negative 2 pi and 2 pi. If you want to go out and look at more periods, that's what it would look like. Right, we're all familiar with that one. Amplitude is 1, right? So the range of this is between negative 1 and 1. Cosine looks very similar to it, right? It's really just a phase shift of sine. Tangent doesn't look anything like those, right? Where is tangent having its problems? Okay, so what is tangent by definition? It's what trig function over what trig function? It's sine over cosine. So anywhere where cosine would be 0 is where we would have a problem, right? So I'm going to take the sine function off the graph. The green is the cosine, right? Everywhere where cosine crosses the x-axis corresponds to a vertical asymptote for the tangent function, doesn't it? Okay. And then if we look at cosecant, what trig function causes the denominator to blow up there? I mean, what's the cosecant is 1 over sine, right? So sine function is the one on the bottom. So anywhere where sine is 0, we should have those asymptotes. So there's your sine function. Notice that at all the x-intercepts, you have vertical asymptotes. All right. I think that's enough. I can go through and look at all these. But those are all functions you should have seen already in pre-calc. Now, because the sine function is not one-to-one, right? It does not pass the horizontal line test. We cannot say it has an inverse unless we restrict its domain. So that's what we do. We restrict the sine function. And I have different ways I could restrict it. Let me do this one. So I'll take the sine out of here. See, this black part is just that first little piece right here. Would that piece by itself, would it be 1-to-1? Yes? Does that piece have the entire range of sine included in it? Does it go from negative 1 to 1 and include all the points in between? Yes? So that would be a valid cut that we could take of the sine curve and define an inverse on that. We could do that. But that's not the only one. We could also do this one over here, right? And we could cut it anywhere we want as long as we get the entire range from negative 1 to 1, and we could define an inverse on that piece. So what piece do we use? You might use one, I might use a different one. So we all have to agree on the cut that we're going to take. And the cut that we take is this one. It's this one right here. And I'll take the sine curve out of there. That's the one we all agree is the one we'll use for the inverse sine. It includes the entire range from negative 1 to 1, so it should work. So the arc sine, so there's different notations we use for this. Arc sine, or the little sign with the little negative 1 up here, is defined if we all agree to restrict the sine curve to the interval negative pi over 2 to pi over 2. Then it'll be 1-to-1 and thus have an inverse. And then here's the notation for it. Inverse sine of x equals y if and only if sine of y equals x. And then this is just different notation using arc sine instead of the inverse notation. So here's what happens if I graph the two together. So the red one is the sine curve, the blue one is the inverse sine, and all functions, when you graph their inverses, does anyone know what the relationship is when you look at them graphically, geometrically? Like how they're related? Like if I say that this is a 1-to-1 function, isn't it? What does its inverse then look like geometrically? It's a reflection of this over the diagonal, which is the identity function, y equals x. If I take this, I reflect it over like this, then that's what the inverse looks like. So you can kind of see that in that picture. If you take the red function and you reflect it over the diagonal, you will get the blue function. Now, does everyone agree now that the blue function on this little piece, because that's it, there's no more to it, that's the whole inverse sine function. Do you agree that it is smooth? and continuous at least there. So I should be able to take its derivative, shouldn't I? I should be able to go to a point on this curve. I should be able to find a tangent line, right? But what is the derivative of it? And that's what this is about. Now, before we do that, more reminding you of how to evaluate inverse trig functions, because they're dangerous, aren't they? Aren't inverse trig functions a little dangerous? Not if you break your calculator out, right? All right, so what is arc sine of 1? And somebody tell me, without their calculator, tell me what you're doing in order to get the answer you're getting. So anyone want to volunteer?
Are you looking for the angle whose sine is on?
That's right. That's it. You're looking for the angle that when you plug that angle into sine, you get 1. So here's another way I could have said this. Let's say that this is equal to something and call it y, right? So we have written up here something like this. Arc sine of x equals y, right? Here x is 1. According to what I had up there just a second ago, this is true double implication, meaning if and only if what sine of y equals x, right? So up here, this should say if and only if, everyone, this is an arrow, double arrow, it's an implication that goes that way and the other way. Okay, that's what this symbol is. I'm just drawing it real fast, I apologize. If and only if sine of y equals 1. So that's what you were saying. We want to find, turn around. Okay, Tony. So Tony was saying that all this is saying is find the angle so that when you plug it into sine, you get 1. Right? So what is it? So what are you looking at mentally here? Are you looking at the sine curve or are you looking at the unit circle? Let's take a vote. How many of you are looking at the sine curve in your head? Unit circle? Okay, good. Unit circle is probably the better thing to look at. How many of you are looking for your calculator? Anyone looking for? Okay, hopefully you're not looking for your calculator. All right. So the great thing about the unit circle is that the points on the unit circle correspond to the values of sine and cosine, right? Cosine is the x-coordinate. Sine is the y-coordinate. So this is saying where on the unit circle is your y-coordinate 1? It's going to be right here. All right, that's where your y-coordinate is 1. And what angle is that? What angle corresponds to that? Right here. 90 degrees. And what's another way to say 90 degrees in radians? Pi over 2. We'll do everything in radians in here. So pi over 2? Yes? So your answer would be pi over 2. Is that the only answer? Like, forget all of this right now. If I asked you what angle do you plug into sine to get 1, is pi over 2 the only answer? No, because I could go around and back, right? Or I could go around twice and back. And what's happening there is you're looking at the entire sine curve and you're saying, where is it 1? And it's happening infinitely many times, right? But that's why the inverse has to be cut. We cut it off, and you can only look between two values, negative pi over 2 and pi over 2. That's the only place you can look. So back here, you're only allowed to rotate up 90 and down 90 if you're looking at an inverse sine. Got it? Again, this is pre-cal stuff, so this is not new material. I would be presenting in a different way if this were pre-cal, right? Any questions? Okay, let's look at the next one, part B. What's arc sine of 3 pi over 2? What is it? Pi over 6. So by me writing this, all I'm doing is just getting you used to both notations, right? Part A, I used one notation. On part B, I'm using the other notation, but it's the same question. This is saying to us that sine of something equals root 3 over 2. So you go to your unit circle and you say, where's the y coordinate root 3 over 2? What was it? Pi over 3. That's all right. Here, the coordinates are 1/2 root 3 over 2, right? You're looking at the y coordinate because this is inverse sine, or this is inverse sine. Is that the only place on the unit circle that the y coordinate is root 3 over 2? How about over here? Isn't that negative 1/2 root 3 over 2? Don't those have the same y coordinates? But what? Why can't I give you two answers then, this one and this one? Because the restriction, right? Because you're dealing with inverse sine function, you are not allowed to look in the second or third quadrants. Your angle can't live there, which means it has to be this one. And that was pi over 3. Okay? So the answer here would be pi over 3. We good? Now, cosine can be done the same way, and tangent can be done the same way. You can cut them, but the restrictions are different. All right, so let's talk quickly about the restrictions so that they don't catch you later. I'm going to give you three different scenarios. If arc sine of x equals y, then what can you tell me about y? It has to be between where and where? Negative pi over 2 and pi over 2, right? So picture-wise, your angle has to come from those two quadrants, yes? Understand that? All right, so if you're dealing with cosine inverse of x is y, then your y must be between where and where? 0 and pi. 0 and pi. So we use a different cut. Let me show you the cut, since not enough of you answered when I asked that. Here's cosine. And what we do is we cut it between 0 and pi. That's the domain we agreed on to cut. Why can we not use the same domain as the sine one? Why can't we use negative pi over 2 to pi over 2? Because in that little range, it doesn't, well, in that little domain, it doesn't include the entire range of cosine. So we can't use the same restriction. So picture-wise, anytime you're dealing with inverse cosine, you can only be pulling your angles from the first and second quadrant. Right? It's got to come from here to here. And what about for arctangent? What is it? Actually, what? It's the same as sine, arc sine. So that's good. You don't have to remember a third one that's different than these two. The restriction for your arctangent is going to be the same as it was for sine. So the angle that it'll spit back again has to come from first or fourth quadrants. There's three others, right? There's inverse secant, inverse cosecant, inverse cotangent. They all have restrictions also. They're found in the book. All right, and that's what I put in the notes. You can find them in the book. They aren't used that much, so I'm not going to list them out here for you. No questions before I move on? I'll point something else out to you. We're not going to have a lot of fun time in this class. I apologize. We're not going to have a lot of like, hey, let's break into groups and let's spend the next hour working on these problems and having fun. Like, it's going to be mostly just like pedal to the floor me lecturing, unfortunately. It's just because of the amount of information that we have to get through. In a class like Cal 1, we can spend a little more time on like group activities and stuff. But like last semester, I ran out of time in Cal 2. I wasn't able to get to Chapter 9, which it's okay, but you know, if I would have slowed down for group works and stuff like that, we wouldn't even finished 8. So just, I don't enjoy lecturing this much because I've been on your end and it's tough. But just kind of know that before you come in here. Come rested and fed, and if you can sleep with your eyes open, more power to you. All right, so what's next? Cancellation property. We got to be careful with the cancellation property. This is abused way too many times. Cancellation property says something like this: sine inverse x equals x. Sine inverse of sine x equals x. Those two properties are correct if there's appropriate restrictions placed on x. I'll give you an example of some proper usage and improper usage. So let's take a look at this first one. As an example of this, what's sine of arc sine of root 3 over 2? That should be root 3 over 2, right? But the only reason that's true is because what? What is the inverse sine of root 3 over 2? We just did that problem? That was pi over 3. And then sine of pi over 3 would spit back root 3 over 2. Right? In fact, it's going to be very hard to trip this one up. It's going to work almost every single time. Look, in fact, it works, it's this first one here. It works as long as the x you're plugging in is between -1 and 1. It will always just spit out exactly what's in here. So these kill each other off. The x falls out, you're done. But then someone will give you something like this because you're not paying attention. And you'll put 2. And that's not correct, right? Because this is saying what to us? What angle, right? What angle on the unit circle or on the sine function gives you a y value of 2? Well, sine's bounded between -1 and 1, so it's impossible. So this can't possibly be 2, right? So there'd be no answer for this. This wouldn't make any sense. But if you put 2, you would be incorrect. All right, so that's the dangerous part of that one. This one is even more dangerous. So let me show you one simple usage or simple application of sine inverse of sine of pi over 3. That should be pi over 3. Because what's sine of pi over 3? Root 3 over 2. Right? We just did that. And then now the inverse says, okay, go back and tell me what angle you got this from. And that's going to be pi over 3. Can someone give me an example of one that would not work this way? Sine inverse sine of pi? Is that what I heard? Pi? Is that just pi? Well, if you don't pay attention to it, yes, you'll think that's what it is, and it's incorrect. Because what is sine of pi? 0. So you're really saying, what's arc sine of 0? And so now this is, all right, where on the unit circle is your y coordinate 0, right? That happens here and here, but wait a minute, we're looking at an inverse. We have to cut these off. So your answer has to be 0, doesn't it? The angle 0. So this is 0, not pi. Just be careful with the cancellation property. All right, now we're finally at the derivatives. All right, so what are the derivatives of these inverse trig functions? We know that we can graph them, And therefore, they should have nice tangent lines somewhere. So let's figure out what it is. There should be 6 of them, right?
Yeah.
To do this, we will have to use a couple of things from the past. Reference triangles and implicit differentiation, which is why I gave you that warm-up that I gave you. So let's try and find, I'm doing example 2 here, if y is equal to the inverse sine of x, I want us to find y prime. I'm going to do this one myself, and the next one I'm going to ask you to do. All right? See if you can follow this. First of all, I cannot just take the derivative on both sides. I can't just say, okay, y prime equals the derivative of this, because I don't know what the derivative of this is. Can I bring the negative 1 down? And no, because that's not a power, right? This represents an inverse function. So there's no rule that we have that we're going to be able to do to deal with this. So what we do instead is we get rid of this inverse part by applying the sine function on both sides of the equation. Okay, so I'm going to take sine on both sides of the equation. Does that seem like a legitimate move to you, like an algebraic move? Does that seem okay to you if I do that? Okay. Now there are some certain restrictions now. I mean, we do have restrictions on x because we know that there are domain restrictions for x, right? But what that allows me to say now is that sine of y is equal to what?
Sine of x? Or x. Yeah.
Sine of arcsine of x, which should be x, as long as what? Well, go back up. What was the restriction we had for this one? As long as the x was between -1 and 1, right? So this is true if x is between -1 and 1. Right? So we're all still good with that? Now, what's the value of me doing that? I mean, what have I gained now?
You can do a change.
Now I can do a derivative, right? Because I know derivative of sine. And so what I'll do is implicit differentiation at this point. Right? So this is a big point in the problem that this is not the answer. I'm just boxing it because we have converted something we didn't know the derivative of to an equation that has things that we can take the derivative of. So let's take derivative implicitly with respect to x, and I'll do it up here. What is the derivative of sine of y? Cosine y times y prime, right? So we have to remember that chain rule. And then equals, what's the derivative of the right side? 1, right? Because we're differentiating with respect to x. And what were we trying to find? Y prime. There it is. Isolate it. Divide by cosine y. Yes? The only problem with this so far is that most of the time in Cal 1, if you have y as a function of x, and you took the derivative, your answer was in terms of x, wasn't it? Like if I gave you y is equal to x squared plus 1, asked you to take the derivative you would have said was 2x, right? So x was in the answer. Here, the answer involves y, not x. So what we'd like to do is get that y back to an x.
So you're
All right.
right. 17 million.
We could replace that y with this right here. We could. Do y'all see that? I could write this. Don't write it though, okay? We're going to do something else. Would you agree that I could do this? And that would be it? Yes? Okay, but we're not going to. We're going to do something a little different. We're going to try and figure out what cosine y is. And I'm going to go back to this thing that I boxed. And I'm going to draw a reference triangle. So what I'm asking you to do right now is draw a triangle that illustrates this equation. So here it comes. Here's a right triangle. The angle in this equation is what? Well, that is, right? But what's the angle in this equation? The x or the y? The y, right? So I'm going to put a y right here. Do you agree that that triangle has an angle y in it? And according to this, sine of y has to be x, which is the same as saying sine of y has to be x over 1. And when you're dealing with trig functions, sine is which side of the triangle divided by which side of the triangle? Opposite over hypotenuse. So the side opposite of this y should be what? X. And the side that is the hypotenuse should be 1. Yes? So that picture goes with this equation. You need to be able to do this a lot in this class. So comfortable with that? Now, what is it that we wanted to know? What is cosine of y? That's adjacent over hypotenuse. Do you know the adjacent side? You can solve for it, right? You don't know it right now, but you have 2 of 3 sides of a right triangle. So we can find this adjacent side? Let's call it A for adjacent. How about that? Let's find what the A is. So A squared plus x squared is 1 squared, which is 1. And so A squared equals 1 minus x squared. I'm just isolating the A squared, moving the x squared to the other side. Finally, square root. Do we need plus or minus? No. We're assuming A is a positive length of the side of a right triangle. So that's A. Let me come back in here. I'm going to just replace it. What we want is 1 over cosine of y, which is the same as secant y. So you could just do adjacent over hypotenuse. No? No, that's cosine, sorry. Hypotenuse over adjacent is secant. Yes? Okay, so our answer should be this over this. So y prime should be 1 over square root 1 minus x squared, so long as the x was between -1 and 1. That's it. That's the derivative. That is the slope of the tangent line. Can anyone see that as long as your x is in the window -1, 1, does everyone see that this derivative is always positive? The numerator is always positive, right? 1 minus a number squared, as long as this number is between -1 and 1, when you square it, it's going to be smaller than 1. So this will give you a positive number always. The square root of a positive number will be a positive number, which means that the derivative is always positive, means the function is always increasing, isn't it? And we showed it up there a little while ago that it was increasing. All right, so I'm going to give you a couple of minutes. Let's see how much further we have here. I talked a little more than I wanted to. You know, I'm going to keep going. I'm not going to let you do one on your own. Sorry. I was going to let you do cosine. So now we know we have a general formula for the derivative of arc sine, right? There it is, right there. But now, right away, we start applying the chain rule, all the rules that we can do with this. So on the next example, we have find the derivative with respect to x of, I want to change this problem up a little bit. Make it, instead of x squared plus 1, let's do 2x squared minus 1. All right, so me doing that thing with the reference triangle and figuring out what the derivative of arc sine is, that's a one-time thing. We don't have to show that ever again. We have a formula for it, right? Now we use the formula for something like this. So we're trying to take the derivative of arc sine of something, right? So we're going to need to apply a chain rule here. The outer function being what? What's the outer function here? The arc sine. The inner function being the 2x minus 1. So again, depending on your Cal 1 experience and how good that was and how the chain rule was, let's see if you can determine this, what this would be. So what's the derivative of arc sine of something here? 1 over the square root of 1 minus x, but x in this problem is not x. It's what? 2x squared minus 1. So that goes here. I'll do it in a different color. 2x squared minus 1, but then squared, right? So that's the formula we just came up with. 1 over the square root of 1 minus x squared. Then chain rule times the derivative of what's in here. Well, that should be clean, right? 4x. That's it, right? And we could clean it up. We put the 4x on top. We could expand this out and nah, just leave it. This is good enough.
And that's how you want it for the rest of the year. You don't need us to clean up, as it were.
This doesn't have much that we would clean. Just the 4 on top. Yeah, that's okay. Yeah, yeah. This is not like with the Cal one where you had to simplify the derivatives and make them look better. Although you will be wishing that's what you were doing again at some point in time, probably.
Do you worry about rationalized radicals?
No, I don't.
Okay.
Yeah. When you're talking, yeah, no, I'm not. But that's a different conversation. I'm sure I will get to it at some point of why I don't look at it as, I have a different perspective on it, I guess. All right, next one. All right, that was, I gave you the derivative of arc sine, right? The others can be found in the book. And they're on your formula sheets that you're allowed to print and bring to class. All right, so don't get caught out next class. I give some pop quiz over what are the derivatives of the inverse trig functions, and you're that one person that didn't bring the formula sheets, right? Because that would be a gimme quiz, wouldn't it? Yeah, so you're responsible for knowing what they are. Anybody have their formula sheets with them? Yeah? So what's derivative of arc cosine? Can you find it on there?
Yeah. It is negative 1 over 1 minus x squared.
It's the same as the arc sine derivative, but it's negative 1 over that. And then there's arc tangent and so on and so forth. Arc tangent's worth us mentioning, though. I will mention this one. If y is equal to the arc tangent of x, the derivative of this, without me showing you the whole process, is 1 over 1 plus x squared. But you could do this exactly the same as I did the other one. You would take what on both sides first? Tangent first, then you would do derivative, then you would do a reference triangle, and you would eventually get back to this. This will be with us until the end of class. This will never go away, the derivative of arc tangent. So maybe a star next to this one because it does come up so much. So I have another example that has some chain rule in it. If y is equal to the square root of the natural log of arctangent x. I'm asking for the derivative. I'll give you like 2 minutes to see if you can do that on your own.
How's your break?
It was good, man. It was good. I was ready to come back, though.
Okay, let me see.
Yeah, it was good, but
Holidays? Change your money? The holidays change your money?
if I want to go buy something every day, you know? That's the way it is. But,
Yeah, I don't think I'm leaving for that 2 weeks thing.
okay.
Remember I told you about last?
Yeah, yeah.
I talked to him and let me stay.
Oh, good.
And I'm like, I'm gonna do it in the summer.
Okay. All right, you get anywhere with this? How many of you think you have it? Show of hands. All right, so if you're going to use chain rule here, how many kind of layers to this onion do we have?
4 or 5.
What would be the outer function? The root. Next one in. Natural log. Next one in. Arctan. So maybe like 3 layers to this. So you start by looking at what's the derivative of the square root of an expression. So what is the derivative of the square root of an expression? 1/2 square. Okay, so depending, again, this is Cal 1, how you learned it. The derivative of the square root of something will always look like that. Okay, always. Now, some of you might do this, and then up to the negative 1/2. That's correct also, but if you were to clean it up, it would wind up looking like this. But what goes in here?
Natural log.
Everything that was under here, right? Natural log arctan x. All right, now chain rule, so multiplication. Now you move into the next function. We've taken care of the square root, so times derivative natural log of something is 1 over it, right? So 1 over arctan x. And then times again. Now the derivative of arctan x, which is 1 over 1 plus x squared. You could also write x squared plus 1 on the bottoms, which doesn't matter. Is that all right? You can't bring arctangent up, right? And say that this is just tangent? All right. It's one of the places in math that really mathematicians should be ashamed of themselves for using bad notation here, right? Because in some sense, sometimes that means that power, a negative exponent, and sometimes it means an inverse. And they're totally different things. So you have to know in the context of how it appears. So that would be it. You could, again, push this all together, make a 1 on top, maybe put the 2, maybe the arctangent right here. You could maybe put that out there in front in parentheses. But that's it. That's your derivative. Just trying to get you to think chain rule. All right, let's try this next one. How about this? Arc sine of xy squared equals 1 plus x times y. And you're asked to find dy dx. So can we find the slope of the tangent line, some way of representing that if we have this equation? So anyone recognize what we're going to have to do here? Implicit, right? I mean, there's no way around that. You're not going to be able to solve for y. And so let's go after it. How about the left-hand side? You're going to be taking the derivative of arc sine of something. And we just came up with a formula for that. So it's going to be 1 over the square root of 1 minus this. What do you call the thing that lives inside of a function? The thing inside it here? It has a name, a general name. Anyone remember hearing the argument of the function? This is the argument of the function. So we're going to do 1 over the square root of 1 minus this argument squared. So xy squared squared. Are we done on the left-hand side? No. Now what we have to do is multiply times the derivative of what's in here, which is going to require us to do what? Product rule. Product rule, right? Because we have a product right there. So we have to do the derivative of this one times this one plus the derivative of this one times this one. Always keep in mind that derivative of x is 1, derivative of y is y prime. So derivative of x, 1 times y squared plus derivative of y squared, which is 2y y prime times x. That finishes off the product rule, doesn't it? For that side. Parentheses. Are these parentheses necessary? Absolutely, because this expression would have to distribute through to both of those, wouldn't they? If I was going to free these things up from the parentheses, that would have to get distributed through to both. Leaving this off is a disaster, right? So, there. Equals. Now, the right side. We have addition separating two terms, so we can do each derivative separately. Derivative of 1, 0, right? Plus, what do we need to do here? Another product rule. So the derivative of x, which is 1 times y, plus the derivative of y, y prime, times x. And that would be your derivative. Now, what would you have to do to get your y prime by itself on one side? This to here, this to here. So it looks something like this. Y squared over root 1 minus xy squared squared plus 2y y prime x over that same root equals y plus y prime x. So all that did was this thing appeared below each of those, right? That's it. And now you have a y prime term here. Bless you. And a y prime term here. So you're going to move those to one side, right? By what? Subtracting this one, bringing it over. Taking this y, bringing it to the other side, so subtracting it. Once you do that, what do? After you've got all your y primes over here? Simplify it, right? So you pull a y prime out, and then you bring all that junk to the other side. So look, this is Cal 1, right? The only difference is that now we are allowed to play with inverse trig functions too. Those can be part of our derivatives. I'll stop here. I want to get to this last example. Got about 8 minutes. Let's see if I can wrap this up. Did the sign-in sheet get around to everybody? No? Okay. You'll hopefully recognize this problem. It's a related rate problem in Cal 1. A rocket is fired straight up with the speed of 1,000 miles per hour. So it's moving, okay, constant speed, 1,000 miles per hour. An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? So you basically have some guy standing there with binoculars on the ground. A mile away is a launch pad. He's looking at the rocket. The rocket is fired. We're assuming there's no acceleration. It's just instantly at 1,000 miles per hour, okay? So there it is, 1,000 miles per hour. He's following it with his binoculars. Exactly when the rocket is 3 miles high, we want to know how fast he's having to turn his binoculars to keep up with the rocket. Understand the question? Okay, so let's draw it with a picture. Here's my binoculars guy. That's my man standing on the ground. Okay? It's pretty impressive, isn't it? Here's my rocket. This is the launch pad. My rocket has been launched into the air. Here's my rocket. Flames. Again. Impressive. I know. I get told that all the time. I'm in the wrong business here. All right, so I'm looking for angle of inclination. So if we're assuming that the guy's looking at the rocket, and we're going to look at the rocket as being a point, right? then we're trying to figure out this angle and how fast it's changing, right? So depending on how you did, and again, how you were taught to do related rate problems, that's going to impact whether or not what I do up here is going to help you or like confuse you. I always tell my students with related rate problems to draw two pictures. One picture is a general picture. It's the picture of when things are moving. And then the other picture is a snapshot picture. It's the instant in time that's in question. So here's the first picture, calling this my general one. Is any of this ringing a bell? I mean, I'm getting some looks like this is the first time I've ever seen a word problem. Not sure if that's just... Are you all right? An instant in question. General picture, instant. What are the things, let's start with the instant one. What are the things that are definitely fixed, not moving at the instant in time? What can I assign values to here? I got what? 3 miles high and 1 mile high. So it's not drawn to scale. Sorry. Right? That's okay. It's still a right triangle. Those two sides are fixed. All right? How about this angle in here? Is it fixed right now in this picture?
Yes, we don't know it.
We don't know it right offhand, but yes, this is an angle, and I'm going to put a little check. I know what that is. In fact, I could find it easily. I could use the fact that tangent theta is 3 over 1, which is the same as tangent theta is 3. Right? And I could take arctangent on both sides and get my calculator out, and I could tell you what theta is. Couldn't I? Yes?
Yes.
All right. So I've got theta here. Here's my general picture. Anything over here that's not changing? A mile away. That's it, right? Is this changing in this picture? Yes. So since it's changing, I can't fix it at 3. I'm going to give it a variable. I'm going to call it y, only because we like x to be horizontal, y to be vertical. That's just a convention we like using. Right? So that's the picture when everything's moving. Is theta moving here? Is theta changing?
Yes.
Yes. All right, so now you try and write down what it is that you want and what it is that you're given. So can anyone help me with this? Either one of these, what I want, what I'm given.
You want the rate of how fast he
I want the rate that, okay, so no, you know how to say it. You want the rate at which what?
The angle's increasing.
The angle that we're calling
Theta.
theta. You want to know how fast theta is changing?
Yes.
With respect to time, right? So we want d theta dt. That's what we want. Now, start to ring bell? Okay. What are we given? Are we given the rate that something's changing? The speed, which represents which variable over here? Y, right? It's this distance, right? How fast is y changing? At 1,000 miles per hour. So we're given dy dt is 1,000, right? Also, what we wanted was d theta dt, but we didn't want it just at any time. We wanted it at a specific point. We wanted it when?
It's 3 miles.
When what was 3 miles?
So the rocket's 3 miles.
Which is what variable to us? Y. When y is 3. So that's pretty much the setup. You draw a picture of everything moving. You draw a picture at that snapshot, that instant in time. You try and figure out what it is you're looking for, when you wanted it. You're trying to figure out also what you were given. Once you have those, you have to try and connect this variable to this variable with an equation. Any equation you can come up with, looking off of this picture, not this one. What is an equation that relates these two together? Theta and y. I didn't hear. Can anyone connect y and theta together? Sine? Sine would be, we would need the hypotenuse, wouldn't we? Which we don't know. But tangent uses y and 1, and 1's not changing, right? So I could use the equation tangent of theta is y. Yes? And then what do? Once you find an equation, take the derivative with respect to time, right? Implicit differentiation with respect to time. This is what you would do in Cal 1. And that's fine. That's the same thing we're going to do here. The only difference is, what was it we were trying to find? Look, d theta dt, right? Theta's trapped in a tangent, isn't it? I can make this problem a lot easier for myself, if I release theta from the tangent. And to do that, I can take arctangent on both sides. And I'm going to do that before I take a derivative. So I'm just going to take arctangent of tangent and then equals arctangent of y. You okay with that? So that just leaves me theta is arctangent y. And now I'm going to take the derivative with respect to time. What is the derivative of theta with respect to time? d theta dt. And see, this is now, the other side is the part you couldn't do in Cal 1. Because what is the derivative of arctangent of something? Well, that's the one I put a star on just a second ago. It's 1 over 1 plus, and in this problem, y squared, right? Chain rule. Now the derivative of what's in here? Y prime, but because it's with respect to time, I'm going to actually write dy dt. Did everyone see that? Derivative of theta with respect to time is d theta dt. Derivative of arctangent of y, 1 over 1 plus y squared, times, chain rule, derivative of what's in here, dy dt. What's good about this? I have everything I need, right? dy dt, right, is 1,000. Y is 3. And I never needed theta. I never needed to solve for it. If you didn't do this and you went and you did it this way, in Cal 1, you would eventually have to figure out what theta is, or you'd have to draw a triangle, or you'd do something. It'd be a little more work. This is just quicker, that's all. But we had to be able to take derivative of arctangent. Sorry, I went over on time today. Everyone is signed in. Let me see if the homework assignment's here. No? Oh, there it is. The homework assignments are usually at the end of the notes. Sometimes I will change them. Sometimes I'll just say, that's good, just do that. Let me just double check it. Page 183. There's 1, 5, 15. Looks good. All right. You should do your homework. That's what all those students said. See you on Thursday. Yes. Uh-huh.
What we just did. And
Yeah, let me turn this off so you don't have to be on video.